So, good afternoon. Those who are in the lecture room and for those who are watching us remotely. Today we have the pleasure to have Professor Ronald Miles to give a talk about the Nanophone, which is sensing sound with nanoscale spider silk. Professor Miles is a distinguished professor and chair of the Department of Mechanical Engineering in University of Binghamton. His research is in mechanical engineering and MEMS devices. He got his bachelor's degree from University of California at Berkeley, but he got his master's degree and his PhD here in University of Washington. So he's a kind of a local person. Also, he worked at Boeing for quite a while. And on top of that, he's not a stranger here in Microsoft research. He gave a talk in 2003 about his amazing work of bio-inspiring modeling, inspired design of MEMS microphones. And we were able to hear an update about this work in 2011. So in 2018, you see it was 8, then 7 years. So next talk apparently will be after 6 years. So my prediction is that in 2024 we'll have Professor Ron Miles again. But for now, you have the floor.
All right, thank you. So I'm going to be talking about sort of it's actually somewhat disturbing a consistent theme of ways of sensing sound, because the first talk I gave was a sort of bio-inspired method of sensing sound. I'm still sort of stuck on the same basic theme, but that work was about a microphone idea inspired by flies, and this one is actually based on spider silk, and a very different approach to the problem, but it's actually addressing a very similar problem that we were addressing then. So I'm going to talk about directional acoustic sensing. Again, localizing sound or figuring out where sound comes from is something that I've been, for some reason, interested in for a long, long time. And I'm going to first talk about sensing that using pressure, which is the way it's done nearly everywhere. And then I'm going to talk about the idea of sensing sound instead of detecting pressure and detecting acoustic particle velocity using thin fibers. And sort of the basic research question that I asked in this project is, if I want to use a fiber to detect the air motion, what should its essential properties be? How thin should it be? How do you construct something like that so that it is driven by viscous forces in the air? The bottom line, if you're in a hurry and you need to go do something else, is that we showed that if you make a fiber that is on the order of about 0.5 micron in diameter, it can turn out to be an extremely high fidelity, high resolution method of detecting sound. So I'll show you those results. And then at the end, I'm going to show a little bit about transduction. The earlier work on this, most of the work on this has to do with using electrodynamic transduction. And I want to also talk about the idea of possibly using capacitive sensing in order to turn the motion of the device into an electronic signal. So, pressure sensing and microphones. You all know what microphones look like. Basically, they consist of a diaphragm that responds to pressure, and then some sort of an electronic gadgetry that converts the motion of that diaphragm into an electronic signal. And I have a belief, or a hypothesis, which can't be proven, but a belief that the reason that microphones look this way is that the people who originally came up with the basic microphone idea, people like Thomas Edison, Alexander Graham Bell, they knew something about how ears work. They knew that there was an eardrum and that inside the ear is this crazy apparatus which converts the motion of the eardrum into an electronic signal, and it responds to pressure. And sound can be detected then using pressure. And basically that's what microphones look like. And I think that they did this kind of copying biology. You know, a lot of work is done these days on biomimetic ideas. I think they did it just because it was sort of obvious to them. They weren't really trying to copy it. They weren't thinking about other methods that might be used to detect sound. And so one of the themes of this is I want to convince you that there are other methods of detecting sound that could have a lot of advantages that are different than the way humans and other mammals do it. So another aspect of sensing sound that's really important, which you know about, is that it's really useful to be able to use, say, more than one microphone and then process the signals in order to determine where the sound is coming from. And this is important certainly in hearing aids. Most hearing aids contain multiple microphones, 2 microphones, and then the differences in the pressures detected by those is then processed in order to determine the orientation of the sound, and this is processed in order to get rid of unwanted background noise. And as you know, if you take a simple pair of non-directional microphones, you can just process the difference in those pressures and you can get a first-order figure-8 directivity pattern. Because of course if sound gets to both microphones at the same time in the same amplitude and you subtract it, you don't get anything, but if it gets to one microphone before the other, then you do get something. And if you plot this on a polar plot, you get this sort of standard dipole kind of figure-8 pattern. So that is a simple way to get a directional output using pressure sensing, pressure microphones. But sort of a problem with that is that in sound, the wavelength of sound, of course, depends on the frequency. So for low frequency sounds, like this one, you have a longer wavelength than this one for a higher frequency sound. And if you sample the pressure at 2 spatial locations with the high frequency sound, you get more difference than you do for the low frequency sound. So this difference output turns out to be strongly dependent on frequency, which is actually really bad. And as a result, these kinds of directional microphones, they sound terrible. That you lose all the low frequencies and you get a frequency response of the output. This is measured output from a directional microphone for hearing aids. You get an output signal that is basically proportional to frequency. And a non-directional microphone, even though it's not perfectly flat, has a much flatter frequency response and sounds better. You could, of course, use a compensation filter to flatten this thing out. That's not difficult, but the problem is that the noise in the microphone starts to become a problem at these lower frequencies. The signal can get buried in the microphone noise, and that's a nuisance, especially at lower frequencies. So this is important for hearing aids, and of course it's also important for smart speakers, and I don't actually know what type of smart speaker this is. I just stole this picture off the internet. But these devices, of course, have an array of microphones, and they have the same problem. And it places stringent performance requirements on the microphones. So the smart speaker manufacturers are yelling at the microphone manufacturers to improve the quality of their microphones in order to improve the ability to detect sound and have this system listen to the person that it needs to. So pressure sensing, I think, has basic challenges. And I believe that microphones sense pressure because humans sense pressure. But the truth is that most animals that hear, in fact, the vast majority of animals that can hear, don't hear pressure at all. They hear air motion. And that's because there are a lot of insects in this world, and insects, almost the vast majority of insects that can hear using hairs. One example of that is a mosquito. Mosquitoes hear using their antennae, and they have very fluffy, especially the males have very fluffy antennae, which will respond to viscous forces in the air. So when the sound wave is coming to them, they detect the acoustic particle velocity, then they don't detect the pressure. In addition, we've also shown that spiders spiders are also covered with hairs, and some of these hairs can detect air motion, and we've shown that they can also detect airborne sound using their hairs. And another animal that's well known to be able to hear is the cricket. And at the back end of the cricket, they have these appendages that are called cerci, and those have little fine hairs on them that respond really well to air motion. And so they can hear using these hairs on their cerci. Now, crickets also have tympanal ears on the front, but it's known that they can hear sound using these hairs on the back. So the hairs are not responding to sound pressure, they're just detecting the particle motion. And I've been interested in sort of biomimetic designs, and so just to go back to the 2003 talk, briefly, I think that we can learn a lot from animals and looking at how animals do things, and that work had to do with studying the ears of this fly, and I'll resist the temptation to rerun the 2003 talk. You can go look at the tape, I guess. But basically, we developed microphones that make use of the ideas that we uncovered in understanding the eardrums of this fly. And the fly it's shown here on a cricket, and that's because the fly is very good at localizing the sound from the cricket. But the fly has eardrums, actually, and that's a very, very unusual arrangement for flies. Most flies are stone deaf. There's only a couple of species known that have eardrums, and so this one is a very special animal. But we worked on ways to commercialize or ways to create devices based on the principles there, and that's because it's based on a fly, which is a fascinating story. A lot of people were amused by this, and there are, I believe, about 44 patents on microphones based on that discovery. I have about half of them, and the rest of them are awarded to people all over the world, universities and companies. And there are a number of research groups continuing to develop microphones based on those ideas. But that has to do with sensing pressure. And I've kind of moved now to be obsessing on the idea of detecting motion of the air. And that's because sound, well, first off, most animals use that method, and they've been doing it for 300 million years. So there's probably something to learn from doing that. And also, sound is, of course, it's not just pressure. Sound is fluctuations in the pressure, but it's also fluctuations in the motion of the air molecules, the velocity of these molecules. It's fluctuations in temperature, and its fluctuations in density. And really any one of those four could be used to detect sound. And humans have obsessed on the pressure. That's because that's what we detect. And that doesn't necessarily mean that it's the best way of doing it in an engineering device. So maybe if we think a little bit about what sound is, and we're thinking about sound in air. So air is a gas, and that means it's just molecules zooming around all over the place depending on their temperature. And this is just kind of a simulation of the motion of these air molecules moving around randomly. And if a sound wave is created in that space, you see this wave front, which consists of varying density of these little particles. But if you were to track an individual particle, it's just moving back and forth. It isn't moving itself. The wave is traveling, but the particles are not. The particles are moving back and forth. So you get this pressure front, a density change, and because the density and pressure are changing, you get temperature. But velocity is something that is certainly could be detected. And people have looked at ways to detect acoustic velocity or flow using MEMS devices. A number of people have created devices that kind of look sort of like hairs. They're the little rods that stick up out of a substrate, and then there's some sort of gadget at the bottom in order to detect the rotation of that rod. And I think it's kind of useful to think about sort of how well these could work by comparing the motion of the moving device, the hair, artificial hair, compare that motion to the motion of the air around it in a sound field. If it moves the same as the air does, I would consider that really good. You know, you want to sample the motion of the air, you want your mechanical device to have the same motion as the air. And so this is a plot of the velocity of a hair relative to the velocity of the air. Again, if it's 1, that's great. And this curve here represents what is known for the hairs on a cricket cerci. So these are natural hairs, and they're known to be pretty good detectors of sound. This curve is sort of the best MEMS sensor. And this point is that it's not very good. It doesn't move nearly as much as the natural hair on the cricket, and it's several orders of magnitude, a couple of orders of magnitude less. So it really isn't very suitable as an acoustic detector. Maybe it works okay for larger flows, but if you want to sense sound, it's not very effective. But it's got to be true that little thin light things move with the air. If you just look at dust flying around in the air and it's very, very thin and light, the air motion changes just the slightest bit, and you can see this thing following the air, and smoke follows the air. So it must be possible to create a very fine device, thin device, that is driven by viscous forces in the air that force it to just move with the air. So I asked the question, if I were to take, instead of to try to create a hair, what if I just take a fiber and hold it at 2 ends and let it be driven by the viscous forces in the air? The question is, you know, how thin should it be in order for its motion to be an accurate measure of how the air is moving in a sound field? The sound field doesn't create much force on it, but the air is moving back and forth. If you put a thin enough fiber in that space, the fiber must be somehow forced by the viscous forces. Yeah?
I was just curious about a question about the sound field, right? So what are other interfering phenomena in nature which can potentially stimulate air velocity other than sound, which might be competing factors with sound? Like, is it temperature? Is it anything else?
Well, I mean, there's wind. You know, there's low, so there's low frequency fluctuations in velocity that would interfere, but they're at much lower frequencies than sound.
So the question is emanating from my curiosity about the reason people might have picked to sense pressure is because its interfering factors are lower compared to velocity. I don't know if that is true. That's what I'm trying to understand.
Yeah.
Because if you're trying to sense velocity change might occur because of sound. It might also occur because of other phenomena.
Well, I think that if you have a fluctuation in the velocity, yeah, it's possible that there could be a fluctuation in the velocity that you would not detect with a pressure detector.
Yeah.
It's possible. But there are also, yeah, so if you're in an open space like this, and there's a sound wave traveling, a plane sound wave traveling, if you have pressure, you have velocity. They're related to each other. So in the vast majority of cases,
They are related.
they are closely related. The pressure and the velocity are in a plane sound wave, which is kind of the normal thing. They're related by the acoustic impedance of air, which is just a constant. Rho, the density times the sound speed, it's like 415 something or other. And so pressure and velocity are closely linked in a free travel.
The first derivative of the pressure as a function of time.
Euler equation, yeah. Pressure gradient, yeah. So they're related, they're brothers. So if you measure one, you can measure the other. There are situations, if you're, say, near a rigid boundary, there won't be any velocity, but there will be pressure. But I actually think,
Also, constant wind will be velocity, but no pressure.
yeah,
Changes in
and
the pressure.
no sound.
And no sound.
I don't know. Yeah, they're different, but I think that the reason that pressure microphones look like that, I still think that it's possible that it's just because it was known that ears in humans have eardrums. Well, make a eardrum in a microphone. You know, it's kind of an obvious thing. And it wasn't well understood that animals with hairs could hear sound too at that time. Anyway, it is still true that the vast majority of animals that can hear don't use pressure.
Do mammals use that?
Mammals do. Mammals have all ears that are kind of sort of the same. But mammals are just mammals. I mean, there's a lot of other animals out there that can hear, you know, just stinking mammals. Anyway, so this basic question is, if I were to take a fiber and I want to detect this air motion, you know, how thin should it be if I want its motion to represent the motion of the air? So I treat the air motion using the simple plane wave, ideal sort of plane sound wave. And if I know the pressure in a plane sound wave, and I assume it's a harmonic wave traveling in a certain, you know, direction, y, if I know the air density and the sound speed, I can calculate the fluctuating air particle velocity. This is just a standard thing. So that's the excitation of this fiber. And I'll think of the fiber as a beam. And I'm mostly a mechanical engineer, so beams are normal to me. And you can model the motion of a beam by simple equation. This is a differential equation, or subscript of x means partial derivative with respect to x. So this first term is kind of the bending stiffness of this beam or fiber, and r is the radius, and E is Young's modulus. So this is the flexural rigidity. These other terms have to do with the sort of tension in this beam. And that also depends on r. Here it's r squared. The bending stiffness depends on r to the fourth. And then there's this mass term, inertia. Rho is the density, and the second derivative, the acceleration of the beam. So the left side of this is just a simple beam model. The right side is the force due to the relative velocity between the beam and the air. And that's due to viscous forces. So that's actually the harder part to calculate because it's a fluid dynamics problem full of ugly differential equations. But fortunately, there's a recent paper by Stokes that he published in 1851 where he sorted all of this out. And he sorted it out actually in terms of a series solution because there weren't functions to express the answers. And since then, his friend Vsilk came up with these functions that can be used to calculate that force. And it was modeled as a circular cylinder, infinitely long with flow. And so there's a nice solution for the viscous force on this beam if it's got circular cross-section. And of course, we're also assuming that the air is a continuum, which at very small scales it really kind of isn't, but you still can get some insight out of this approximate model. And so this gives a relation between the force and kind of the relative velocity between the beam and the air. And so to sort out like how thin should this beam be in order for its motion to represent the same motion as the air, you can actually sort of see it just by looking at the differential equation without solving it. If you look at the terms on the left side, those all have to do with sort of the mechanical forces in this beam. And as r gets small, r to the fourth gets really small, and the rest of the terms go with r squared. So as r gets small, those terms go with r squared, and then it's the right-hand side. So how does the right-hand side vary with r? And unfortunately, R appears inside these Bessel functions and out here. And unless you're a special person, it's a little hard to see exactly how the Bessel functions go. But it turns out that the viscous force is actually more, you could think of it as being proportional to the surface area of this beam. And the surface area goes with like 2 pi r. So it's more like r instead of r squared. The left-hand side stuff is more like the cross-sectional area as opposed to the surface area. And actually, this viscous force, it's even a weaker dependence than r. It's more like the square root of r almost. So the viscous force is a really weak function of the radius. So what that means is, as r gets small, the left side of this equation gets really small, really fast. The right side doesn't. That means that the left side has got to be, if the left side is small, I mean, the viscous force doesn't depend so much on r. The only way the whole equation can be satisfied is if the relative velocity between the fiber and the air, that's got to be small. Which means that the fiber moves with the air as r gets small. And actually, that's a ridiculously complicated way of saying that small things float around in the air. Because you can see, you know, ever since you were a little kid, you could see that. But this kind of adds an ability then to sort of do some calculations. If the model is reasonable, we can do some predictions. And again, just using this relative velocity, the force, you can solve that equation and express it in terms of the eigenfunctions of this beam. And so you can do calculations and estimate how the response of this thing varies with the material properties, with the radius. And so we had this equation in this model, and I wanted to check out this to see if it compared any reasonably well with experiment. And so I went looking for thin fibers and thin wires. I had some 25 micron diameter wire bonding wire, which according to the model, it was way too thick really to get anything reasonable. And so I went looking for thin wire on the internet. And I found a source of 8 micron stainless steel wire. And I requested a quote from the manufacturer, and the quote came back $25,000. And I said, thank you very much. I mean, if I were here, I would have just bought it, I guess. But, you know, I'm at a university, so we don't have that kind of money. So I kept looking, and then I found a source of 6 micron stainless steel wire from Blue Barn Fiber on Etsy. And they use this, they spin it into wool and make conductive yarn. I don't know. But it's 6 microns, which wasn't quite as thin as I wanted, but I bought it for a bag of it for $15. And I think they made $14 a profit, but that was cool. I don't know. So you can get this stuff, and it's pretty nice. It's very, very fine, and it's fairly strong because it's stainless steel. And so we placed this in our anechoic chamber, and actually that picture I took this wire and soldered it at two ends of other wire, normal sized wire, to hold it, and then this is a laser vibrometer dot to measure its motion. Placed this in our anechoic chamber with a laser vibrometer and played sound to it. And also, before I talk about that, I just want to put in a little bragging about our anechoic chamber. I know you guys have all kinds of anechoic chambers that are really fancy. We have a really nice one as well. It's not as quiet as the quietest one you have, but it's the quietest one at a university. And we have a robot that will move a microphone around the chamber, and we are able to make measurements at basically millimeter steps if we want. This is an 80 hertz cutoff chamber, and it has a 0.5 dBA noise floor. So it's a very, very quiet. And so these are some sample directivity measurements that we could make using the robot around a loudspeaker. So that's just an aside, bragging. But so we were able to measure the vibration of this wire and compare it to the predicted result. So this is assuming a 6 micron diameter wire, 3 centimeters long. The red curve is the prediction of the response of the velocity of the wire relative to the velocity of the air in the sound field as a function of frequency. And if you sort of squint at this picture, you can sort of see that the curves kind of sort of look like each other. It's not perfect because this wire is not a perfectly straight thing and the boundary conditions are complicated, but it made us think at least that we're headed in the right direction, that this model might represent the truth somehow. And so the model also enables us to play games with the diameter of the wire, or the radius, and see how thin should we make it in order to get the kind of frequency response we'd like. So these are just calculated results. This is the velocity of the wire relative to the velocity of the air for the 6 micron wire, and it's got a really complicated frequency response because it's basically got waves that are reflecting off the ends, and you know, it's not ideal for detecting sound. But as you reduce the diameter of the wire, the viscous forces tend to dominate, and you can see these resonances kind of start to get damped out. And eventually, if you drop the diameter down to 10 to the minus 7 meters, you get a pretty flat-looking response. And this is assuming properties of stainless steel. So this is a stainless steel wire, you know, 1/10 of a micron in diameter. It looks like it has a pretty flat frequency response. So I had exhausted sources on the internet for finding thin wire. I think 6 microns is about as small as I could find. And I wanted thinner stuff to test, something less than a micron. And so I have a friend in our chemistry department. They work on electrospinning, and this is a way to make really fine fibers, and a lot of people are doing this sort of thing. So they were able to electrospin us some PMMA, which is a plastic sort of material, and that had a diameter of about 1/2 micron. And this is an image of some PMMA fibers, which you can sort of see here. They're suspended between little ridges on a piece of aluminum foil. So this was electrospun onto this sort of corrugated or wrinkled up aluminum foil. And we're just sort of waving your hand at the stuff. And you can see that it moves around really easily with the air. And it's kind of like fibrous smoke almost. You know, it just moves really, really easily with the air. So we got some data for this electrospun PMMA, and it looked super promising, had a nice flat frequency response, but it was kind of a hassle to work with because it was kind of delicate. And one day, my grad student, Jen Zhou, was walking in the Binghamton University Nature Preserve, and he noticed spider webs. And the spider web obviously was getting blown around by the wind, and insects could land on it and it wouldn't fall apart. And he thought it would be really, really thin and strong. So he borrowed a spider from the Nature Preserve and brought it to the lab. And he figured out a system. He never gave the spider back, actually, but don't tell anyone. He figured out a system for harvesting silk from the spider. So he used a couple of sticks, basically, let the spider drop, and as the spider falls, they will send out web. And so he would basically drop the spider and sort of collect the web, the silk off of the spider. And so now we have boxes of spider silk in the lab, and a lot of spiders also. He was breeding spiders in the lab. Anyway, so the spider silk that we got could vary. It depends on the spider, but we got some, here's an SEM image of a strand of spider silk that is about 700 nanometers in diameter, and we've tested it down to about a half a micron, 500 nanometers. So it's a source of fine fiber, and it's actually easier to get than the electrospun PMMA, and it's much stronger. It's easier to get because a spider gives it to us, which is great. So we tested that, again, using the same sort of setup with a laser vibrometer, measuring the motion of the velocity of the spider silk relative to the velocity of the air. And we obtained extremely flat, uniform response from 1 hertz up to 50 kilohertz, which is really kind of unprecedented for detecting sound. And this, again, is the comparison showing what the cricket can achieve, as well as the best existing MEMS sensor. So this is sort of a, nerny kind of bragging plot, showing significantly better performance than previous man-made devices. And the reason that it works well is that the diameter of the silk used in this curve is about 700 nanometers. The cricket cercel hair is about 7 microns in diameter, and the MEMS sensor is about 44 microns in diameter. So it's really more like a telephone pole in comparison to spider silk. So if the spider silk is thin enough, it reproduces the motion of the air with extremely good fidelity. Checking out our analytical model, using spider silk, we could get silk that was different diameters from different spiders and compare the predicted with the measured motion of the silk. And actually it looks pretty promising that as you change the diameter all the way up to 3 microns, the model continues to agree pretty well. So it means we're pretty confident that we can estimate how thin this material ought to be in order to do a good job of detecting sound. So those results are all actually just the motion of the silk relative to the motion of the air, and obtained using a laser vibrometer, where we're shining a laser light on this fiber and detecting its velocity with that. And that's actually not a very great way to make a microphone, because the laser vibrometer costs like $100,000, and it's not very practical. So we wanted a way to get the motion out of this silk without using the laser. And the simplest way of doing that was to make this fiber conductive by putting a very thin layer of gold on the spider silk. So we put about 80 nanometers thick layer of gold on one side of the spider silk using an E-beam evaporator, and then make it conductive. Then you place it in a magnetic field, and then the velocity of this silk relative to the magnetic field will produce an open circuit voltage across the ends of the fiber. But it's just simply the magnetic flux density times the length of the conductor times the velocity of the conductor produces an output voltage. And so this is a plot of the electrical output obtained by this. Now it's a microphone. It's a electrodynamic microphone compared to the velocity of the air in the sound field. And again, this case, it shows really flat response from 1 hertz up to 10 kilohertz. At higher frequencies, because we use a magnet next to this thing, we get sound reflections off the magnet. So the package causes the higher frequency response to look uglier, but that's really just a matter of how you arrange the magnets around it. Since this device is detecting velocity is a vector, it also then can produce a directionally sensitive output. So if you imagine the little fiber is oriented like this, and if you have sound coming normal to the axis of the fiber, you get a signal, but if the sound is propagating parallel to the axis of the fiber, it's not going to respond. It doesn't have any force. And this is true at virtually any frequency. So we set up a special apparatus to actually measure infrasound, create a uniform field at super low frequencies around this little fiber microphone. And so this is data obtained at 3 hertz. And then we could orient this fiber at different angles relative to the sound. And this is a plot of the time domain response. So when the fiber is normal to the direction of propagation, we get a lot of signal, and then as you orient it so that the fiber is parallel, you don't get any signal anymore. And this is a sound with a wavelength of about 114 meters. So we are able to localize sound at subsonic, deeply subsonic frequencies using this simple fiber detecting apparatus. This is an impossible thing to do with pressure microphones, unless they are many, many meters apart. This is a device that's on the order of a centimeter. And it works at higher frequencies as well. These are audible frequencies. We placed this little fiber microphone on a rotation stage and made measurements of the output at a couple of hundred different angles. And it has a figure-8 directivity pattern, which is maintained across the audible range. At really high frequencies, again, the magnets and the housing start to affect the directivity pattern, but the amplitude and the shape of this polar pattern is maintained uniform across all frequencies. And again, that's something that can't be done using pressure microphones. So like I said, if you do this kind of directional sensing using pressure microphones, at low frequencies, you don't get much signal, and at high frequencies, you get more signal, and that causes the frequency response of those things to go up with frequency up until you get to the first resonance. And our microphone has a flat response, basically. So what we also then put this in the anechoic chamber, set up some loudspeakers, and recorded the electrical output of the microphone, just to sort of see what it sounded like. So we played music out of the loudspeaker and then recorded it using the Vsilk microphone, and also recorded it using a sort of conventional hearing aid microphone, which is basically a pressure gradient microphone, so that it has this kind of response. And hopefully I can play this and it'll work. Okay. So this is recorded using the Vsilk microphone. And this is a sample using the hearing aid microphone. So it does not sound as good. And that's just because all the low frequencies are gone. So this idea we published a bunch of papers on this, and it got some press, and a company was formed in Canada, company called Soundscrit, and their aim is to basically commercialize this idea. And they put together a little demo that they presented at the Consumer Electronics Show in Las Vegas in January. And I don't know if anybody from Microsoft contacted them, but they've received a lot of interest from the major companies creating smart speakers. And so I'll just give you a little video that they put together demonstrating the performance of their own prototype. This particular prototype contains fibers or wires that are oriented in 2 directions, and it's a device that sits on a table, and in this demo it shows that this simple little directional device is able to sort out the sound from a couple of different speakers. So I'll let them explain it. Hopefully it's going to work. Okay.
Hi everyone, we're Soundscrit, and we're really excited to share with you a really neat microphone technology that we've been working on. Inspired by some small insects that have an incredible ability to sense sound using just their hairs, we've been able to develop a microphone that can separate sounds coming from multiple directions simultaneously. So to illustrate this, Stefan and Aman are going to talk into the microphone from different directions, and we'll take the raw audio output and feed it into Google Speech Recognition. What we'll see is that we can transcribe speech from both of them without any crosstalk, and this is done all in hardware. So let's see how that looks.
I really like this microphone because it only listens to me and no one else. I only wish that people were like that too.
Okay, so now let me go. All right, why does it keep doing this? Hold on. Okay, so all right, so that is on basically creating a device that operates using this principle of detecting air motion instead of pressure. And I mentioned that my grad student borrowed a spider from our nature preserve, and actually he's and I are both kind of interested in animals, and so there are interesting questions about how animals use this. And one question was that since spiders make webs, is it possible that the whole spider web can detect sound? And so my student was kind of obsessed with this question and decided to try to gather a spider web and place it in our anechoic chamber and make laser vibrometer measurements of the motion at lots of locations. First, he had to get a spider web. And to do that, he noticed that there were a lot of spiders that were creating webs outside of our building. And at night, a lot of insects would come to the window, and there was a light shining in the hallway, and these insects were coming to the light, and the spiders were putting their webs there and catching them. And so he built a little wooden frame that looks like this, just a rectangular frame, and he placed this up against the window, and the spiders then would create their web on this frame. And then in the morning, he would come along and steal the web. And he brought the web into the lab and set up a fixture to hold the web and have a reference microphone near the web, and placed this in the chamber with the laser vibrometer on a positioning stage so that we could move the laser dot anywhere we wanted on that spider web, play sound at it, and make measurements actually at about 1,000 locations on this spider web. So he's kind of obsessed. It was an enormous amount of work to make all those measurements. All this was by control. Fortunately, there's a camera inside the laser, and you're able to aim this thing at all kinds of locations on the web and track their positions accurately by measuring it using the rotation or using the positioning stage. So playing sound at various frequencies, you can see the motion of the web. This is animated from the measured data. Again, 1,000 measurement locations all over the web, and the spider would normally be here. So at 100 hertz, the whole web is just moving in and out. And at higher frequencies, it moves in a more complicated pattern. And still higher, it gets more complicated. But the motion in the middle stays pretty representative of the motion of the air in the sound field. So it appears that the web is actually moving pretty well in the sound field. And he also played sound out of the loudspeaker and measured the sound field using a reference microphone, and then converted that. Because it's basically a plane wave, we could also calculate the velocity of the air in the sound field. And these are traces showing the measured velocity of the air, and then this is measured using the laser on the spider web. And these sounds are a wing beat from an insect, a cricket call, and then a bird song. And so I'll play the sound that basically is the sound that a spider might detect if it were sitting in the middle of the web. So this is the velocity of the web. So that's just the motion of the web. So it's possible that spiders could hear sound using their web. Of course, we don't know if the spider can actually use this, but the web is certainly moving. So these fine fibers can definitely move with the sound. So the idea behind using the fiber, of course, and having it be very, very thin means that it's got to be really, really compliant, really easy to move, really flexible, so that the mechanical forces in the fiber are dominated by the viscous forces. And we used electrodynamic transduction by just putting a magnet next to it and measure the voltage. That's really, really simple. But using electrodynamic transduction means you need a magnet. And if you want to commercialize this or mass produce it, the magnet's a hassle. And the other problem is scaling of the length. The length of the fiber needs to be long enough to get a good voltage. And so sort of as another related thing, a question is it possible to incorporate capacitive sensing to detect the motion of these very, very fine, viscous-driven things that are moving with the air? And the motivation for that is that all microphones, basically, all the microphones you folks would have any interest in are capacitive. And that's because capacitive sensing, you can shrink the size. If you design things right, it can scale down and mass produce. So the question is it possible to use capacitive sensing on something that is so flimsy and light that it moves with the air? And that presents a problem because capacitive sensing means you have to apply a voltage between two things, turn the voltage up, and you get an electronic output. But the trouble with the voltage is that it also exerts an attractive force on things. So in a microphone, if you use a parallel plate capacitor, you turn up the bias voltage to get a good electronic signal out of it, but there is an attractive force that pulls the diaphragm toward this back plate, and the diaphragm has to be stiff enough to avoid being pulled into the back plate. This is a problem for all capacitive sensors. So it seems kind of incompatible to use capacitive sensing on something that is so wispy and compliant that it can be moved in the air. So I'm sort of reluctant to even talk about it just because it's almost another subject, but it relates to the idea of using this sort of viscous-driven compliant thing using capacitive sensing. So I'll spare you the details. You can go look it up in a paper that was published in June where we created an alternate way of creating a capacitive sensor. Basically, the idea is if you imagine a pair of electrodes, say the green are electrodes that are held at 0 volts, and a moving electrode, the red guy, that could respond to sound and is driven by viscous forces in the air, you apply a bias voltage to that. As it moves, it creates a difference in charge on these two electrodes. And if the system is designed right, the electrostatic force on this red thing can be extremely small in comparison to its own mechanical forces. And it's kind of a subject of another talk, but just to give you the basic idea, we took this sort of arrangement with a moving electrode like this that's made using a very thin mylar. It's got like almost no stiffness. It's almost like a hanging pendulum. And had a couple of fixed electrodes that were hooked up to charge amplifiers. So the voltages of these two green electrodes was basically held at virtual ground by these op amps. Measured the sound near the device, played sound out of a loudspeaker, measured the motion of the moving electrode with a laser vibrometer, and also detected the output using these two charge amplifiers. Played sound, and the sound, here's a fairly loud sound, about a Pascal peak to peak, or peak amplitude pressure, and measured the velocity of this device, and it tracks the sound pressure. And the outputs of those two electrodes are actually out of phase because of the way the thing moves, and you get a significant amount of output voltage. This is about 1/4 of a volt peak, and if you subtract these two outputs from each other, you get about 1/2 volt out of these things. So this is basically a microphone with a sensitivity of about 1/2 volt per Pascal. And the microphones that are available commercially in cell phones have a sensitivity that's about 10 millivolts per Pascal. That's considered to be a pretty good microphone. And this is about 50 times that sensitive. And in addition, the bias voltage that's applied to that compliant electrode has virtually no influence on the electrode's motion, which is also very different from a parallel plate capacitive arrangement. So this shows the frequency response of the motion measured using a laser vibrometer of this moving electrode, which is a super compliant thing driven by the air in the sound field with different bias voltages applied. And we tried a wide range of bias voltages and kept cranking up the bias voltage to see if it would have an effect. So starting out with no voltage applied at all, that's this purpley guy. And then as you increase the bias voltage all the way up to 400 volts, it doesn't have any influence on the motion of the electrode. This is very different than any other type of microphone. So the electrostatic field is not influencing the motion, even though this electrode is super compliant. And the electrical output also, it doubles when you double the bias voltage, which makes sense. So the concept is that you could make a very, very compliant, flimsy electrode driven by air, viscous forces, and still use capacitive sensing, which I think could be much perhaps easier to commercialize and mass produce than electrodynamic, and compatible with MEMS. So, to summarize, the primary innovations from this is basically to use a viscous force. This is an approach to sensing sound that has kind of been ignored for over 100 years in technology for measuring sound. Use a very, very thin compliant element. With that idea, we're able to obtain a flat frequency response from infrasound to ultrasound. This whole device could be made very small. It has a first-order directivity pattern, first-order gradient directivity pattern, and we're able to localize low-frequency sound in a very small space. The other thing about this electrodynamic sensor is that it's passive. It doesn't require an energy source, a bias voltage, if you don't use capacitive and it's just a magnet. You could even use it as a nano generator. And then came up with a potential method for incorporating capacitive sensing in this device. So with that, I think I probably used up my time. Have any questions? More questions? Yeah.
You just reminded me of something with the spiders and the different frequencies when you play the insects. Did you see a paper maybe like 4 years ago or so where it was found that spiders kind of tune their silks to different frequencies so they can triangulate like where an insect impacts?
Yeah. Yeah. And we actually have another paper that is about to be submitted showing that the tuning, how the spider itself can tune the web for acoustic detection. But yes, it's possible that the spider could be doing some actively tuning of it in order to maximize the sensitivity at certain frequencies. Yeah, it's... Yeah.
Spider silk is a liquid crystal polymer, and there's a lot that goes into that. There's 3 companies in the world that are trying to do this artificially. Vsilk in Germany, Spyber with a B in Japan, and one other in Germany who I can't remember. Have you considered trying to compare your locked up spider in your lab
Yeah.
and her friends and to those that are commercially available?
I would love to. I haven't really tried to get some of their silk, but that would be certainly well worth doing. Maybe you could give me details on if you know who these people are.
Sure.
We haven't tried to make contact with artificial silk suppliers.
So going on that theme, not all spiders are the same.
Yes.
It's like not all conditions are the same.
Yeah.
So you mentioned temperature. Liquid crystals are, there's a lot of things that go into a liquid crystal polymer.
Yeah.
Temperature is one. Did you, how do I phrase this? I want to be politically correct to all those around PETA. Did you subject to the spider's environment to different conditions, i.e. humidity and temperature, to see if there was variations in their frequency or in the response?
No. However, we did look at different materials. So it turns out that you could make this fiber out of almost anything as long as it's thin enough. And we have results of predictions that we've published in, I think, the PNAS paper, where we simulate the frequency response of silk or fibers made with all kinds of different materials, carbon, steel. All that really matters is sort of how heavy it is. If you use lead or something really heavy, then you need to make it really, really thin. But if it's made out of a material that has a density that's kind of on the order of water or plastic, you can change it to all kinds of different materials, and it really makes almost no difference in the frequency response. And we've measured spider silk, and we've measured PMMA, and gotten the same answer.
But your equations, Euler's equation, had modulus in it, so one would presume.
That's right. But all those terms that multiply the modulus, they go with r squared, or r to the 4th.
Oh, and you're saying that's dominant?
And when r is small, they just go away. And all you're left with is the right side of the equation. So basically, if you make it thin enough, it just has to move with the air. And you don't care what you make it out of. And we've shown that that's true.
All right. Well,
So-
I want to throw something else out at you. So the Chinese came out with a paper 2 years ago that was really interesting in that on the mulberry leaves, they deposited deliberately carbon nanotubes and fed those to the spiders.
Yeah.
And while the mass differential was slightly different, the modulus was significantly different.
Yeah.
Which was pretty revolutionary if you think about it.
Yeah.
So how do you think that would impact?
So I think as long as you don't have significant tension in the silk, if you bring the ends in just slightly so that it's kind of slack, I would maintain it's not going to make any difference. And you can kind of see that if we go back, hold on, mouse, all right. So if we go back to the equation, hold on, this equation, no, you can't see it. Hold on. Okay, this equation. So the modulus shows up here. This is the bending rigidity. So in your case, if you throw some nanotubes in there and crank up the modulus high, but if you keep it slack, if you reduce the tension, this term here will be very, very small, so you won't worry about that, and you'll only be left with the bending stiffness. right? If it's a half a micron in diameter, R is 0.5, 10 to the minus 6, and you're making it to the 4th power. So I would maintain you can stick some pretty stiff material in there, and it's not going to make any difference.
Fair enough.
Okay? So, yeah.
What is causing your frequency response to trail off over 50K?
50K, probably the mass of the fiber. At some point, the inertia of the fiber itself starts to be measurable compared to the inertia of the air that is moving with it. So another way of looking at the design problem is what we really want is this thin fiber. If you imagine a bunch of still air and a moving fiber, the viscous force causes the air around the fiber to move with the fiber. And if the mass of that air is greater, a lot greater than the mass of the fiber itself, then the fiber will end up moving just fine with the air. But at some higher frequency, it turns out, I think, that the mass, at some point, the inertia of the fiber starts to play a bigger role. And it eventually does taper off. And that...
For a given material, if you cut the cross-section in half, you should get better frequency.
Yeah. You make it thinner. Like if you use lead, you just have to make it thinner. Or gold.
So directivity, pattern, and frequency response are just two of the parameters of a microphone.
Yeah.
Another parameter we look at is the total harmonic distortions, which exactly is pretty much a consequence of that question. If there is a certain non-linearity in this vibration, we'll get distortions. Have we measured what are the distortions of this microphone?
Have we measured it? Not really. We have a belief about what would cause it. And basically, if you imagine taking this fiber and allowing it to be kind of slack so that there's no initial tension, and now come in here with a very low frequency sound, like 10 hertz, which would have large deflection. The fiber is going to be deflecting a lot because the air is moving a lot. And if the deflection of the fiber gets big enough so that it's no longer slack and it suddenly becomes taut, you're going to get distortion.
Kind of hitting a soft clipping.
Yeah, it's like a clipping thing. And I believe that's going to happen mostly due to very low frequency sounds, where the displacement is great. And I think that's going to be the main source of nonlinearity. It could be, though, that, we've been talking about fibers attached at each end, but you could make other structures that will be driven by viscous forces. They don't have to be attached like that. So I think it depends on the mechanical motion of the device. Is a significant source of how the nonlinearity is. You could make it cantilevered in principle or hanging, and then you're not going to have that problem. But the truth is we haven't really measured it. It's kind of a interesting problem, but we just haven't done it.
What sound pressure levels were you exciting the fiber at?
Like a Pascal or 80 to 90 dB in that kind of range, and a lot of the work had to do with measuring the motion using a laser vibrometer, and the laser needs it doesn't have a super low noise floor, so you need to get some pretty good motion. It's a little tricky to make the measurement with the laser because the laser dot is like this and the fiber is this little thing. So it takes a little bit of work, but...
Figure 8 microphones are not the most commonly used directivity patterns. In real recording and sound capturing, people more frequently use cardioid, hypercardioids, which is in general a combination of figure 8 and an omni microphone.
Yeah.
Any ideas how to create a variable or at least cardioid directivity pattern on supracardioid?
With just the fiber?
Because technically, if I had a MEMS microphone near that fiber, I can do whatever I want.
Exactly. And you know, in my mind, actually going back to, was it 2003, whatever? I mean, in thinking about directional microphones, the way I've been thinking about it is, the hard part is not the pressure. The hard part is the pressure gradient, right? Or the velocity.
Sure.
So I figure, you know, the pressure, we know how to measure pressure. You can just get a microphone, right? I mean, there's lots of microphones that will measure pressure. And they're small and they're not bad. The challenge is, how do you get the gradient, or how do you get that figure 8 that you want to use to combine with the pressure? And so I really haven't tried to figure out how you could take this idea and turn it into a cardioid. But I do have pending IP that enables pressure measurement with this. So it is possible to use the basic idea as a pressure microphone, not a velocity microphone. But that's kind of another seminar. Maybe next time.
Not in 6 years.
Not in 6 years. No, that would be sooner. But yeah, the theme is, you know, and if you want to make a good microphone, you've got to sample the motion of the air. You really want a way to kind of follow all those air molecules and then convert that into an electronic signal. And so there are a lot of ways to do that, other than just making a pressure-sensitive diaphragm.
More questions, colleagues?
One more.
Go ahead.
In your electrodynamic model, did you try to move air with the strand?
No. Try to move the air.
Not to move the
Yeah,
fiber.
Use
just
it
to
as
move the fiber and see if I could move the air with it.
Yeah.
Didn't try that.
It'd be interesting to look at because it's the converse of the theory that makes it work.
I know. How I would have to measure the air motion.
Well, for sure you can make this thing to swing.
Yeah,
The question
I
is,
could-
it is not going to produce a sound.
it's not going to sound like much.
Right. Well, it's not going to move much, right?
Yeah, and I mean, turning it into a loudspeaker, you know, turning it backwards and putting a current through it to drive it, that would be interesting. However, current, you know, you need a bit of current in order to get much force, and I want it to be really thin, and thin things don't like a lot of current.
Right.
So I'm kind of thinking that I'd probably break it really fast if I hooked it up to an amplifier. So I kind of didn't take that idea much further than that.
No, I mean,
It's an interesting thing to try.
be destructive in first experiments at least.
Yeah.
More questions? Let's thank our speaker then.
Okay.